Every day the media talk about criminal facts that require forensic science. Forensic scientists collect scientific evidence at the scene of the crime and analyze it in their laboratory. What happens when the crime involves nuclear materials? Nuclear forensic experts steps in. Nuclear forensics is a relatively young scientific discipline. It's a subdiscipline of classical forensic which aims to characterize radiological or nuclear materials and determine their origin. As classical forensic science, nuclear forensic relies on the fact that certain measurable parameters are characteristic for a given material. These parameters are known as signatures. They are a set of data which reveal unique information about the nature of the material under investigation. These signatures may help to identify the origin of the material, the processes it underwent, and subsequent history. Since the world of possible origin is large, it is usually not sufficient to determine a single signature, such as the isotope ratio of the sample, but by determination of many such signatures, the origin can be narrowed down more and more. For example, the trace elements within the sample and the age give important information about the origin of the sample. These parameters can be determined not only by radiometric measurements, but also with techniques typical of material science and classical forensics. The interpretation of the collected data is a deductive process, which requires a comprehensive knowledge of commercial and military fuel cycles to associate different signatures to a specific origin. First, based on initial analytical results, hypotheses are developed. These hypotheses need to be confirmed by additional measurements, which further corroborate the signature of the sample. In an ideal case, the first hypothesis will prove consistent with all the results. However, this is seldom the case in practice, and often initial hypotheses must be rejected or adjusted. Although there were reports on this field back in 1945, the early 1990s are considered to be the actual birth of modern nuclear forensics. With the breakup of the Soviet Union, a new form of criminal activity, the so-called nuclear smuggling, came up. At borders, illegally obtained radiological and nuclear material were increasingly seized. Identifying and characterizing illicit nuclear material is in the interest of nuclear security and non-proliferation. It aims to gain knowledge about the origin and traffic route of the material. To this purpose, seized material was examined in detail for the first time in March 1992. The first seized nuclear material, Find 1, was analyzed at the Institute for Transuranium Elements in Karlsruhe. It consists of 72 uranium pellets which were intercepted in Augsburg in Germany. The scientists were able to establish that the material was fuel pellets from a Russian Gryphon-type reactor. Moreover, they were able to delimit 2 nuclear facilities in Kazakhstan and Russia from which the fuel could originate. However, at that time, data interpretation and source attribution relied only on the expertise of fewer senior scientists and non-legible individuals. Later, an international cooperation among national laboratories was initiated, and in 1995, the Nuclear Smuggling International Technical Working Group, ITGW, was founded. The working group conducted the first round-robin tests for the characterization of illicit nuclear material and thus contributed considerably to the further development and international standardization of nuclear forensics. Today, the scientific discipline has broadened its application field. For example, to assess the origin and history of environmental samples, the isotopic ratios of different radionuclides present can be determined. As you can see in this picture, the relative abundance of plutonium isotopes are very different for the fallout from atmospheric nuclear weapon tests and from an accident in civilian nuclear power plant. It is possible to identify the isotopic signature of micrometer-sized fuel particles released into the environment, for example during the Chernobyl accident in 1986. With background knowledge about the loading and operation of the reactor, it is even possible to determine the time the so-called hot particle was irradiated in the reactor. Another application of nuclear forensics is nuclear safeguards. The object of nuclear safeguards is to verify the peaceful use of nuclear materials. In order to ensure that nuclear facilities are not misused for purposes other than the declared peaceful use, independent measurements are carried out. The measurements of, for example, isotopic ratios of the fission products are designed to detect derivations from the declared use of the facility and thus prevent proliferation of unauthorized nuclear material. Depending on the sample and the analytical questions, a nuclear forensic scientist has a wide array of analytical tools at his hand. These techniques can be sorted into three broad categories: bulk analysis tools, imaging tools, and microanalysis tools. Bulk analysis tools include mass spectrometry or conventional X-ray fluorescence analysis to characterize the elemental and isotopic composition of the sample. As already mentioned, the isotope ratio of different radionuclides is an important parameter for determining the origin of the sample. The further elementary composition of the sample can give indications about the source. For example, if the sample contains steel, its composition can narrow down the area of the production. Imaging tools like optical or electron microscopy provide high-resolution images which can help to identify inhomogeneities in the material. Even macroscopic parameters like size or weight can tell a lot about the initial use of the sample. In the case of Find 1, the physical dimensions of the uranium pellets were used to determine the reactor type for which they were intended. If the sample is heterogeneous, microanalysis techniques like microEDX are used for further investigate the sample. Bulk analysis techniques applied to a heterogeneous sample can easily lead to misinterpretations. Some of these tools are destructive techniques. Therefore, the material examination must be considered properly. As we can see, nuclear forensics not only has a large field of application, but solving a forensic challenge also requires a broad knowledge about various scientific disciplines. Further, interdisciplinary cooperation at national and international level is essential for its development.